Okay, so today we have Sung-Soo Kim tell us about gauging Zn discrete symmetries of 5D SCFTs. Take it away.
Okay, thank you very much. Just 1 second. Very sorry. So my colleague Hicha wants to come, and he requires me. Okay, so thank you very much for inviting me to this Quiver meeting. And then today I'm going to talk about this gauging of GN discrete symmetries of 5D superconformal theories. This work is done with Hicher, Kim, and Kim Young Lee. Maybe they may come join us soon. Okay. So we are interested in this discrete symmetries of type IIB 5-brane webs. This discrete symmetry is a special discrete symmetry which is generalized the rotations on the PQ 5-brane web together with the SL2Z action. So here, what I mean by rotation in SL2Z action is that the rotation changes the orientation, and the SL2G changes these H charges. For example, here I have the 5D SU2 gauge theory with the Chern-Simon level 0. It has a G2 discrete symmetry, which is a 180-degree rotation of PQ 5-brane web, and together with the changing their charges, which is a Z2 charges of, and this is a part of SL2Z transformations. The same theory also has a Z4 discrete symmetry with a change of the 5-brane wave shape, and such that this 90-degree rotation, and together with a Z4 SL2Z, that it has a Z4 discrete symmetries. So another example is SU2 with two fundamental flavor. It is given in a conventional way here on the left. So this is a conventional 5-brane web for SU2 with a 2 flavor. It's difficult to see actually that whether there is a Z2 discrete symmetries. But if we choose a axial dilaton field tau to be 2 pi e to the 2 pi I over 3, then this 5-brane web can be seen more Z6 symmetry manifest way. Okay. So, okay, so here, 5-brane web has a Z2 or Z3 or Z4 or Z6 symmetries. And in fact, these symmetries can be regarded as zero-form symmetries acting on the particle spectrum of the Coulomb phases of the 5 SCFTs. Here I have an example of the previous example. Okay, how do I? Sorry. So previous SU2 with a 2 flavor. So this theory is known to have the E3 symmetries, which is made out of SU3 with SU2. So here I put some Kähler parameter associated with their BPS state. In fact, these symmetries can be realized as the changing the state associated Q1 and Q2, Q3 in a G3 symmetric ways. This is actually realized as the Y together with the Kähler or Kähler parameter. Somehow is automatically changing the slide. Y1, Y2, Y3 are the fugicities of SU3, and U is the fugacity of SU2. And these Q1 to Q6 actually is transformed to one to another along these G6 symmetries. Now I'm going to, so in this talk, we are going to discuss the resulting 5D superconformal theories arising this Z-n folding or S-folding. So along the way, I may say that gazing Z-n symmetry. So precisely what I mean is a Z-n folding of this, or also known as S-folding. And then I'm going to present some of the resulting theory is a 5D superconformal series. And then in this talk, I will present a systematic prescription or systematic way to deal with this G-n folding and their outcome theories after this G-n folding. So I'm going to also mention that for 5D T-n theories, there has been papers, in particular this Acharya and Lambert and Najar and Svanes and Tien, and they worked on these 5D Tien theories and the gauging of these discrete symmetries. And we are also inspired by this work. And there is some also related work on T3, also Tien and Wang. So, sorry. Here is a plan of my talk. So I'm going to first review this 5D superconformal theories, and it's a 5-brane realization of these theories. And then I'm going to introduce 7 branes to these 5 branes, which makes the 7-brane analysis much joyful and useful. And then I am going to talk about this Z-n folding of these discrete symmetries based on 5-brane ones. So there are 2 classes of this. So depending on the fixed point of the 5-brane this Z-n rotation, whether this is on the face of the Coulomb branch or on the edges or vertices. So we split into 2 classes, and I'm going to talk about these 2 classes and how to do the Z-n folding of these symmetries. Then I'm going to introduce a various examples, in particular, not only 5D, but also 6D series and some KK series. Then I will conclude. So before I move on, if there's a question, you can ask me, or I will continue. Okay. So 5D superconformal series, probably everybody probably are also very familiar with this 5D series. But nevertheless, let me set up the my notation and conventions. So n=1 supersymmetric gauge series of the some gauge group G. It has A supercharges. It has a space-time symmetries of SO4, 1, and also has the R symmetry of SU2. And the particle contents of this 5D supersymmetric series, there is a vector multiplet denoted by AU, mu, and phi. It has so it is a vector field. I mean the gauge field, and it has a scalars and the real scalars. And it consists also with the fermionic partners. It also has a hypermultiplet, which is denoted as a SU2 a double R-symmetric doublet Q, and it's a complex field, and it's also supersymmetric partners. So in the moduli space, there are Coulomb branches and Higgs branches. In particular, I'm going to today I'm going to talk about this Coulomb branch physics. But this Coulomb branch physics, Coulomb branch is parameterized by the vacuum expectation value of vector multiplet the scalar field phi, and on the other hand, this Higgs branch is parameterized by the BEV of the hypermultiplets. So this super there's something that okay. sorry. How do I go back to? Okay, so certain class of 5D, this superconformal supersymmetric gauge series have non-trivial fixed point at UB. It has been drawing a lot of attention recently. In particular, at the UV fixed point, there's interesting physics going on, which is the global symmetry is enhanced. Where in the fixed points, everything is massless. This massless hypermultiplets and massless these instantons, they form bigger representations, and then therefore giving rise to a enhanced global symmetry. And particularly interesting example is SU2 theory with the NF flavor. NF hypermultiply in the fundamental representation. So I'm going to call it flavors. From this NF flavors, the global symmetry is SO to NF, and also in theory there is instanton conserved currents which give rise to U1 instanton numbers, and together they form a NF plus 1 global symmetries. So for example, here, this is the thinking diagram of the red one is coming from the flavors. Instanton is interacting with this spinor representation, and at a fixed point, they form a bigger the representation, make the ENF plus 1 thinking diagrams example. Okay, so along this Coulomb branch, where all the gauge group is broken to U1 to the rank of the gauge group, this theory is described by the abelian low energy effective theory, which is characterized by the prepotential. This prepotential is given in this form, which is one loop exact. There's a term associated with a coupling. So M0 is inverse a coupling squared. And this the first cubic term has to do with the Chern-Simon term. The only this term only exists for the SUN gauge theory, where the n is bigger than 3. And these are the one loop contribution. And the first term coming from the vector multiplet, and the second term is coming from the hypermultiplets. So the example of this prepotential can be written in a very simple form. In particular, in the massless case, the SU2 with the NF flavor is the cubic term is made of 8 minus NF over 6. And in the SU3, Chern-Simon level 0 is this is another example in a chosen to the Weil chamber where it's given here. Okay, so having this prepotential also give rise to some physical observables by taking derivatives on this prepotential. So if we take the first derivative on this prepotential with respect to the Coulomb branch parameters, which is the vacuum expectation value of the scalars in the vector multiplets. So this first derivative gives rise to a magnetic monopole tension, which I'm going to denote by Ti. And the second derivative gives effective coupling, which is plays a role of a metric on the Coulomb branches. These quantities also have some geometric meaning from the perspective of Calabi-Yau geometries or type IIB five-brane waves. So from the geometry, this superconformal theory is realized as an M theory on a non-compact Calabi-Yau 3-4 with some compact cycles shrunk to a point. There, the M2 brane wrapping 2 cycles like this one, where the SU2 is realized as a local P1 cross P1. And these here there's a 2 cycles. This 2 cycle is basically equivalent to the BPS, the particles, and the N5 brane wrapping a 4 cycle, which is this rectangular one, and the volume of this is basically is a monopole string tensions. So also from the 5 brane point, let me also discuss a 5 branes perspective. So the 5 brane is coming from the type IIB string theory, and the BPS configuration is made of the D5 brane and S5 branes and their bound state. Here, because I'm going to extensively use the 5 branes, let me set up my conventions. So here is a world volume directions, and S5 brane is extended all the way to from 0 direction to the 5th directions. The 5 brane is expand in the 5D world volume, and but then extended to a 6 directions. And then 1,1, their bound state is extended on both 5th direction and 6th directions. And the 7, 8, 9 direction is basically equivalent to SU2R symmetries. So I'm going to draw the diagram on this this 5th direction and 6th direction in this way. So the vertical direction is 5th direction, where the NS5 brane is extended. And the horizontal direction is 6th direction, where the D5 brane is extended. And they are making some bound state, which makes a 5 brane web. And it's also a called PQ 5 brane web. And this plane is therefore called PQ planes. Here, these 5 brane wrapping these compact phases give rise to monopole strings. And the area of this compact phases is basically monopole string tension. But recall that this string tension, monopole string tension, can be obtained by taking the derivative on the prepotential. From this 5 brane web point of view, this monopole string tension can be obtained by just computing this area. So in having area, we can now take the integration over this Coulomb branch parameter. Then we can reconstruct the prepotentials. Okay, so introducing the 7 branes on the 5 brane web it reveals a lot of new physics. I mean, the interesting physics is, in particular, the 7 branes actually is extended in the world volume direction 7, 8, and 9 directions, which appears on the 5 brane web as a point, just like a point. And the location of 7 branes does not affect the 5D physics. So we introduce 7 branes at the end of by adding the 7 brane on the 5 brane this tip in this way. And the 7 brane has the monodromies. So monodromy code, we have to always keep them together this way. Here I have some example of SU2 theory with the Chan-Simon discrete theta 0. Here I introduce 7 branes with the same charge, and the another 7 brane with the same charge as the 5 branes. And having these 7 branes, we can do some interesting some manipulation, one of which is Hana-Newton transition or Hana-Newton move, which is bring this one to the inside to here, and then put the 7 branes all together. In particular, this give rise to a systematic way of seeing the global symmetry of theory, which I'm going to talk about now. So to read off the global symmetry from the 7 brane configuration, let me first call some of the frequently appeared 7 branes in this way. So A brane is denoted, A brane is the 7th brane with a charge 1,0, or the 7 branes. B brane is has a charge of 1,-1, and C brane has charge 1,1. And I'm also introduced N brane, which is a 0,1. So this particular combination of 7 branes has to do with the ADE singularity structure, which in 5 brane appears as a flavor symmetry. For example, SUN, a flavor symmetry, arises when 7 branes are arranged such that there are n A branes. So basically, there are n D7 branes are arranged. And SO2, SO2N symmetry arises 7 branes configuration with NA branes together with B and C. And EN symmetry arises A to the n-1 and BC, BC. So N here can be 6, 7, 6, 7, 8, but also from 1 to 5. And the E1 theory to E5 theory has to, is defined in this way. Okay. So it is also useful to understand the 7 brane when you change the 7 branes, rearrange 7 branes, how their charge changes under the monodromies associated with the 7 branes. For example, a 7 brane has a monodromies matrix. It's given if the charge of the 7 brane is PQ and the monodromy matrix is here I denote by K PQ, which is given as like this. So rearranging 7 brane in a counterclockwise way, if I have a 2 7 brane charge R, S and P, Q, and then I put it in this way. Suppose that I want to rearrange their location. So because both have the branch cut, if I move the first one going across the cut of second one, and then the first 7 brane charges changes according to this monodromy relations. And the inverse is basically the same. We just use the inverse matrix of the monodromies. As a result, one can see that the 7 brane AB is same as NC or BN. In particular, this ABC is a BCA, etc., etc. These can be used to have the to read off the 7 branes and then corresponding global symmetries. Okay, this is some explicit example of the 7 brane, of all the 7 brane inside the 5 brane loop. The first one is the local P2. And the second one is on the local P2, we introduce one D7 brane, which is A brane. And then after rearranging the 7 branes, one can see that this configuration is equivalent to this configuration, which is the SU2 with the Chern-Simons discrete theta angle pi, or E1 tilde theories. Adding more flavor or introducing A brane, one can see that the genetic configuration of SUN with N-1 flavor can be written this way. But having this is precisely the ENF, the global symmetry, which I denoted earlier. This is A N-1 BC. So here A N-1 BC in a counterclockwise way. This, by looking at this theory, we can see that this theory has a ENF minus ENF E and global symmetries.
Sung-Soo?
So yes.
So when you have several braids like this, you could have many ways of rearranging.
Yes.
The number of rearranging becomes larger and larger the more braids you have. And so I'm just wondering, in how many different configurations can you read the global symmetry, and how much work is needed in order to figure out what's the most convenient way of writing down the braid system?
I think it depends on the probability rank. Rank 1 case, I think you try to aim for this EN configuration because the EN is biggest the global symmetry. And if you are not able to find, then probably you look for the SUN symmetry.
So that requires. So it requires some trial and error, right? It's kind of a guesswork because you don't really know what. So if you know the answer, I guess you aim towards some brain system that you already know from before. If you don't know the answer, it's I guess it's just a trial and error. No?
Right, I think so. Yeah. So another strategy is to have you do a various Hahn-Witten transition and try to see some subgroup. You may see the subgroup of the enhanced global symmetry. And in that way, you may infer that there may be a bigger symmetry than what I can only see.
I see. Mm-hmm.
For example, here the 7-brain configuration is only limited to ADE global symmetries. Mm-hmm. So suppose that you have a 5-brain web, which you know the global symmetries of SP. Then what you can see is only the subgroup of SP,
I see.
which is ADE type.
I see. Mm-hmm.
Mm.
Okay, thank you.
Okay, thank you. So, okay, so as an explicit example, I'm going to take the SU2 with a 6 flavor. So here I introduce the 6 flavors or A brains or D7, 6 D7 brains. And then, as I earlier mentioned, that A brain is going through BC without any problems, like here, A brain going across BC, so it doesn't change any charges. So 3 of the these 7 brains I can put on here, and I do the Hahn-Witten transition, pulling out all the 7 brains, and make the configuration that has a Z2 symmetries. Okay, so in fact, I'm going to talk about this one a little bit more later. Okay, and now so with these 7 brains, you can rearrange the 5-brain web as such that they may show more explicit discrete symmetries. So, for example, here the local P2 has these Z3 symmetries. So this one has a Z4 or Z2 symmetries. So this a 2 flavor has a G6 symmetries, and 4 flavor also has a Z4 symmetries. And this is also known as T3 symmetry. T3 theory has also G3 symmetry, etc., etc. So here, I also want to mention that SU2 theory with A flavor, which is known as E string theory on a circle. This, in fact, can be arranged to have all the ZN symmetries. For example, this is given as a SU2 with 4 flavors here and 4 flavors here, which is manifestly showing Z2 symmetries. This one is complicated looking at this, but you can think of it as this one as a local P2 with a 9-point blow-up, which each blow-up is written in this way. And also it can be given in this way or other way. And they all have a Z2, Z3, G4, G6 symmetries. So it's very interesting that SU2 with A flavor has all the discrete symmetries. Okay. So let me now also make some comment on this type 2B string axial dilaton. With this axial dilaton, the tension of PQ5 brane web is given as the multiple of the tension of D5 branes. Conventionally, we choose tau to be this I, which makes the tension of NS5 brane is the same as tension of D5 branes. And also 1,1 brane looks like also like the slope is like this. So therefore, their charge conserving configuration is somehow natural. So many of the diagrams that I have shown is based on the choice of this axial dilaton to be I. But different choices, in fact, it makes the some discrete symmetry manifest. Here, if I choose this tau axial dilaton field to be e to the 2 pi I over 3, and then this local P2 given in with the choice of the tau equals I, it is converted to the 5 brane web given looking like this as a Z3 symmetry is manifest. So other choice, for example, tau to be e to the pi I over 3, one can see the Z6 symmetry manifest. So I'm not going to talk about now the gauging this discrete symmetry as a ZN folding of this. Before I talk about, is there any other questions?
I have a question.
Oh, yeah.
Sorry, hi, it's Neil.
Hi.
You said that, can you go back a page?
Yes. Yes.
Yeah, you said that, that checking these values of tau makes the ZN symmetry manifest, but I would say the ZN symmetry requires taking these values of tau.
Oh, that's actually, a true state. Yes.
Okay,
right.
thank you.
Right. Yeah, I agree. Yeah, completely agree. Sorry. I think it was a wrong statement. Yes.
Thank you.
Can I go? Okay.
Yeah.
So then let me move on. So as an example of this Z2 folding, so I have made an example of a Z2 discrete symmetries. So by Z2 folding, I mean those faces those faces are mapped to each other under this Z2 symmetry should be identified. And then by doing so, this volume of the faces will be reduced by half. And naively, one can see that this folding can be achieved by inserting an O7 brane, O7 minus plane to the fixed point of the Z2 symmetry, because O7 minus is sort of the point-like projection. In fact, this is not sufficient because the O7 minus has only the deficit angle of pi over 3. Because of this deficit angle, actually the 5 branes where the O7 is inserted can be distorted. But in order to realize the D2 discrete symmetry and thus their folding, we need a deficit angle of pi, and so we need the asymptotic 5 brane configuration near the fixed point. Their charge should be maintained, and then after this G2 folding. So these can be achieved by adding or inserting 4 more D7 branes. So these together with 07 with the 4 D7 brane, actually they give rise to correct deficit angle as well as the resulting monodromes. Therefore, the 5 brane is not distorted, and it can be these faces can be identified. Also, 5 branes also naturally identifies. So 07, we know that it can be resolved into a pair of 7 branes like a B and C, which is 1, minus 1 7 brane and 1, 1 7 brane. So this Z2 folding is equivalent to inserting the A to the 4th, which is a 4 D7 brane, and BC, which is coming from the 07 minus 7 brane at the fixed point. So the here the folding is done in 2 ways. The first thing is that we cut the 5 brane by half, and then insert this some particular 7 brane configuration. In this case, a D4 to the fixed point. And as a result, the theory can be given as another the 5D superconformal series, which I'm going to discuss more explicitly soon. So this is only for the G2 case, but other GN case like a G3, G4, G6 symmetry can be also straightforwardly generalized. The idea is saying we divide this 5 branes by n slices. By n slices mean that those are a map to each other under the Zn symmetry. So we're dividing these 5 branes n slices, and there is a fixed point of the Zn symmetry, and then we insert a particular 7 brane configuration to the fixed point. The particular configuration has the correct deficit angle and axial dilaton field, what just Neil corrected me, and then corresponding monodromy. And these are the summary of 7 brane configuration. For Z2 folding, we just mentioned that we need to have a D4 the configuration, 7 branes. And G3 symmetry, we need to insert the something associated with the Z6 singularity structures, and the corresponding deficit angle is 4/3 pi. And the axial dilaton field should be chosen to be this way, and the monodromy matrix is given. And Z4 is to do with the E7 structure, and Z6 is also has to do with the EA structures. And then basically, if we have a Zn, and then we slice, we divide the 5 brane of n slice and inserting these D7 branes according to the Zn symmetries. Okay. So earlier I said that there are 2 classes of the 5 brane web. In particular, when we insert the 7 branes into this fixed point, this is these 2 cases is the fixed point exists either on this face of the Coulomb branch, or sometimes it exists in the edges or vertices. So this is 2 possible cases, and the way that we treat this Zn folding is slightly different. So I'm going to talk about one by one. Let me first talk about these cases where the fixed point exists on the face of the Coulomb branch. Okay, so our prescription is as follows. So we are going to cut the n slices. These are the examples of the C2 and Z3 and Z4 and Z6 symmetries. We choose a fundamental domain to be left and bottom. And then we are going to identify these 5 branes. by inserting the 7-brane configurations. And the 7-brane configuration, as I earlier mentioned, that depending on the ZN symmetry, we input D4, DE, E6, E7, E8 symmetries, and that will identifies the this part to this part, and this boundaries to the other boundaries, etc., etc. Okay. So it is also interesting to check in some other way, which is the study of the prepotential. So in general, in a generic point of Coulomb branch, of course, the ZN symmetry is broken. But we are looking at the special point of the Coulomb branch where the ZN symmetry is realized. And then suppose that I have the original theory, which I call T. And the theory after this ZN folding, I'm going to call T divided by ZN. And then one can easily see that the rank of the Coulomb branch dimension is reduced by basically by 1/n. But here we have a -1 and +1 is because usually these Coulomb branch faces in this Coulomb branch faces identifies, and therefore the number of faces is reduced by, like in this case, a half. But when there is a phase, then this Coulomb branch still remains. So when we divide by 1/n, when we divide by n, so we have to take into account the middle part, the center part. This is basically taking into account the center part. So we first remove as if there's no center part and divide by n, and they introduce the center part. So this is how we see the Coulomb branch, the rank of the Coulomb branch after this ZN folding. The flavor symmetry can be also read off. So here, the original Coulomb branch, the original flavor symmetry I denote by R sub F of T, and +3 is in fact is total number of 7 branes, and this total number of 7 branes is reduced by n, and then we are going to insert the 7-brane configurations, and then so the sum of the 3 of the 7 branes should be removed. 2 of them are basically putting the location of 5-brane configuration, and there's one more 7-brane is used to charge conservation. So this is removed by charge conservation. So here the RF of the singular 7-brane singularity that we are inserting is, as you can see, that the rank of this 7-brane is actually 4. So it's because the 2 of the 7 branes here will be used to fix the position of the 5-brane configurations. So it has been already taken care of. This basically in this way, we can obtain the rank of the flavor symmetries. So having this analysis of the Coulomb branch after this ZN folding, the prepotential can be easily obtained by just dividing the original Coulomb branch by n with the identification of the Kähler parameters that are mapped to each other under the ZN action. So it's quite easy to find the prepotential of the ZN folding. So I think I'm a little bit quite late. How much time I have actually?
I think very good. You can just continue.
Okay. Thank you very much. So let me go over some of the examples. So this is a SU2 with the 0 hypermultiplex. So it has a Z2 symmetry. So we cut it 5 rank by half and insert the D4 singularities here. And then after resolving the O7 minus, and we will get a configuration like SU2 with a 4 flavor. 4 flavor is coming from this inserted A branes. Okay, so this is basically the result, and the resulting 5D theories by Z2 folding of SU2 with the Chern-Simons levels discrete set angle 0. So I'm going to do the same thing with from the prepotential point of view. So setting the gauge coupling to be infinite or the M0 to be 0. So the 0 flavor means that NF is 0. So we will have a 8 pi Q, and Z2 folding means that we basically there's nothing to identify, so we just divide by 2, and then it gives you 4 pi to the cube power, and this tells that NF is 4, which is a consistent. So prepotential analysis and 5-rank web the analysis is a consistent. So Z2 SU2 with the Chern-Simons level 0 also has a Z4 symmetries. I basically do the same thing, but in this case, the inserted 7 brane should be associated with the E7 symmetries. So E7 symmetry is there's a 6 A6 and BCB, and that makes SU2 with the 6 flavors. So the analysis or same result can be obtained by looking at this prepotential. So basically, we are going to divide the original prepotential by this 4. That makes this resulting theory is a 2, 5 to the cube, which is 8 minus 6. So this is a 6 flavor again. So the prepotential studies and the 5-rank analysis is consistent again. So this is another example of the, this time is the Z3 folding. This is local P2. And then, so we choose the left bottom part as a fundamental domain and insert this 7-brane configuration associated with a G3 folding, which is an E6 case. And then the configuration, the resulting configuration gives rise to SU2 with a 5 flavor, which is T3, also known as T3 theory. In the same way, we can actually confirm this theory from the prepotential analysis. So we can go on and on. So in particular, the SU2 with the 2 flavor has a Z2, Z3, Z6 symmetry. They are all can be checked from the 5-rank web as well as prepotentials. So this is a summary of a rank 1 theory. Here, this is the original theory. And these are the possible ZN symmetries. For example, we just discussed that local P2 has the G3 symmetries. And then as a result, we see the E6 symmetries. But for rank 1 theories, we know that E6 symmetry is coming from the NF like a 5 flavors. So we can identify that the resulting theory is SU2 with the 5 flavors. So in this way, we can read out all possible rank 1 theories. So another particular, yep.
What's the symmetry that commutes with the subgroup of E that commutes with those discrete symmetries?
You're asking the discrete, the subgroup of this EN symmetry that commutes with the Z3 symmetry?
With any of those Z symmetry. So in each case, there is a subgroup that commutes with the action of the discrete group.
I think in some cases this GN symmetry arises as the ZN Bayer action of these EN symmetries.
In some cases, it's a subgroup of the Weyl group.
Yes, some cases.
So there's some embedding problem over here, right? Because you want to check what's the precise embedding of the discrete group and what's the residual symmetry, continuous symmetry.
Okay. So for the time being, probably I cannot answer clearly your questions.
I see. Okay.
Okay. Thank you. Thank you for the question. Let me just make one comment, which is the EA theory, which sorry, it's E string theory on a circle, which is SU2 with A flavor case. And earlier I said that this one has all the ZN symmetries. And in fact, after this ZN action, this theory is coming back to itself. So it's a self-ZN invariant theories. And it is also, in some sense, the mother theory of all these ZN symmetries. For example, if I decouple a flavor in such a way that maintain the ZN symmetries and is consistently obtained. For example, if I start with an 8 flavor and I decouple the 2 hypermultiplet such that Z2 symmetry is maintained, then I will get the SU2 with the 6th flavor. And again, the reducing 2 more flavor to maintain Z2 symmetry, then I will get the Z4, 4 flavors, and the corresponding theory is basically the E7 symmetry, and then also likewise E6, E5. So the decoupling 3 flavors starting from this SU2 with 8, this flavor, maintaining a Z3 symmetry, I will get the E8, E7, E6, and by removing the 3 hypermultiplets in a ZN invariant way. So this is also interesting the observations. So higher rank generalization is, I would say, this straightforward. So basically we cut the 5 brain by half, insert the corresponding 7 brains, and read off the corresponding these theories, which also it can be also done from the prepotentials. So let me go to the more interesting examples. So which is a TN theory. So the 5-day description of TN theory is a linear quiver with each n have a different the flavors, n flavors on the one side, the other, and then the rank is reduced 1 by 1, and on the other side we have the 2 flavors. The rank of Coulomb branch is n-1 times n-2/2, and then the corresponding 5 brain is like some honeycomb type, where there are n external 5 brains on this one side and another side and the other side. So it has the SUN times SUN times SUN global symmetries. So some of the example is T3 theory is this, T4 theory, and T5 theories. Now we are talking about the ZN folding of TN theories, but again, some of the fixed point exists on this face, some of them exist on the vertices. So we will treat them separately. So first, I'm going to look at the T3K theory and their Z3 folding, which is the case where the fixed point exists on the face. So if I insert, as I done before, inserting this E6 7-brain configuration associated with the Z3 symmetry, then I will have the resulting theory of this Coulomb branch rank is given like this. The flavor symmetry is reduced to SU3n times E6. here we can see that E6 is coming from the insertion of the E6 7 branes. And this SU3K is basically because of G3 symmetry, they are all identified and reduced to just SU3K. This result agrees with the these Acharyas and Niels and others paper. There's no problem with this. So for lower rank case, this theory can be further, the flavor symmetry can be further enhanced to the bigger symmetry. For example, T3 case is the case where SU2 with a 5 flavor, and this Z3 folding gives rise to a 7 these flavors, which has EA symmetries. So here this SU3 times the E6 is enhanced to EA. Yes. Okay, there's also the various examples, which I call these XNN theories and also cross-slash theories, etc., etc. The idea is it is straightforward, although the 5-brane configuration may be a little bit complicated. One can do the same thing as before, inserting the corresponding 7 branes, and then get the resulting 5 branes. Or one can do the prepotential analysis, and they all agrees. So now I'm going to discuss the this ZN folding, where this fixed point exists along the edges or vertices. This probably is one of the interesting things. Before I move on, is there any other questions? Okay, if not, let me continue. So these are the examples of the ZN symmetry, where the fixed point is located along the edges or vertices. So in this case, the inserting a prescription is exactly the same. So we insert a 7-brane, particular 7-brane associated with the ZN symmetry. It's just like the same as the first class, which is on the face. So like Z2, Z3, Z4. One notice is that the here there's no Z6 symmetries. Whenever you try to make a Z6 symmetries, and then you will see that there's a Coulomb branch arises, which that goes back to the first class, which is on the fixed point on the face. But the difference is that when you insert this 7-brane configuration on the edges or vertices, because it's ending on the end point of edges or vertices, one of the inserted 7-brane must end on the edges or vertices. This is make the analysis very interesting. So let me give some example. So this is an example of SU3 with the Chansan level 0. This has discrete Z2 symmetries. So as before, we chose the fundamental domain to be the left side, and we inserted the corresponding D4 symmetries. And then here we have 4 A's and then O7 minus or BC 7 branes. So as I said, one of the inserted the 7-brane configurations, one of the 7-brane in the inserted 7-brane configuration should end on this line. So this the line is now a 1,0 brane, so D5 brane. So it should be ended on this A brane, which is a D7 branes. So this is the point that should be treated very carefully. So the other inserted 7 branes is not attached to any of these, so they can be treated in the same as the case on the face before. But as this A brane is attached to the phi brane, we can do some Hahn-Newton transitions. So by moving this A brane to the left, and then phi brane changes because they are going through the cut of this A brane monodromy. And then the important thing is that in this case, these connected D phi branes in the middle, D phi brane, and painted in red one, is basically annihilated because of the Hahn-Newton transitions. So therefore, I am left with the A brane, which is not attached to any of the phi brane configuration. So by taking this A brane all the way to the infinity to the left, then I can basically decouple this decoupled hypermultiplet, or I can completely remove this A brane. So then I left with this configuration. So originally, I inserted the 7 brane configuration associated with the D4 singularities. So one is expected to have a D4 symmetries, but because of this Hahn-Newton transition and decoupled hypermultiplet, I no longer have D4 symmetries, but I rather have the lower symmetries. But in this example case, I have the E4 or SU5, the global enhanced symmetries, and the resulting theory is SU2 theory with the 3 flavors. Okay, I think that this is an important the part of this the analysis on the second class, where the fixed point is located in the vertex or line. Is there any questions about this?
I have a general question, which is referring to all of those constructions. In perturbative string theory, we have 2 types of Z2 projections. One is an orbifold, one is an orientifold. And because it's perturbative, we can identify that there is an action on the worldsheet or there's no action on the worldsheet. Can you say in these cases whether this is like an orbifold or an orientifold?
Sorry. I think it was not very clear. That can you repeat?
Yeah. So I said that in perturbative string theory, we have 2 types of Z2 projections: the orbifold and the orientifold. Right? Where in one of them there is an action on the worldsheet, and in the other doesn't involve. And the consequences are quite significant, because in one of them we get open strings that follow some unitary pattern, and the other we get quivers which follow orthogonal symplectic. So can you tell what's going to happen in these cases?
Okay.
Is it an orbifold or an orientifold?
I think it's a generalization of the orbifold.
This is orientifold. So you have to flip the string orientation on the word. Sorry.
You think there is it's an analog of an orientifold? Sung-Soo thinks.
Yeah.
Okay, I see. So if we look further into those brane systems, we'll find some sorts of symplectic orthogonal or generalizations of those.
Yeah, exactly. You can stay oriented for the 7 brane there. So before you resolve it, you have oriented for the plane.
That's for the Z2, I see.
So you mean this O7 minus?
Yeah.
Mm-hmm.
And for the case of is the tau parameter fixed for the case of Z2, or is it
Z2 is not fixed. The tau parameter is not fixed for the Z2.
So you can go to a very weakly coupled regime. For Z3, you have to fix it.
You have to fix, yes. Z4 you fix. Z6 also fixed.
And so in orientable planes, you would typically have action on space-time fields, like the B field with x and x minus sign. Do you see anything like that?
Probably I cannot answer this question.
Okay. Good. Thank you. Thank you.
Okay, so let me move on. That's where I am. Okay. So
sorry, just one question before going on.
okay.
Is just a curiosity. When in the 5D perspective, what's the interpretation of the string tau parameter?
I think string parameter doesn't do much. I think in the 5D perspective.
Okay, yeah. Because if I want to study, say, a 5D theory, and I want to integrate this kind of orbifold or antifold machinery, is there a way to see it without, say, a PQ construction? And also the fact that you have this enhancing for special values of tau, can have that 5D field theory interpretation?
So particular, the tau parameter is to have the ZN symmetries. But the 5D theory itself, I think, I mean, the PQ5 when it can be, the shape can be changed, but I think the 5D theory itself probably doesn't affect it much.
Okay, thanks.
Okay, sorry, that probably is not a very satisfactory answer. Let me continue where I am. Okay, so I just discussed that the case where the fixed point exists along a line or the vertices, then we need to take into account. So we need to take into account these 7 branes that is attached to these lines or vertices. And now we can do also check this result from the prepotential point of view. In the prepotential point of view, actually, is rather simple. We identify the field that is permuted under this ZN action and just divide by one n, and then we will get the prepotential for this ZN action. And the rank is also simply divided by n. And probably one needs to a little bit careful about the flavor symmetry, because we need to take into account whether there is Hana-Newton and whether there is a decoupled hypermultiplier or not. And this K parameter is either 0 or 1. If there is a decoupled the 7 branes, and this will be a 1, and the other one is same as before. So just a small caution about this. The prepotential analysis and on a Coulomb branch will be also straightforward. So let me let me then give the explicit example of this ZN folding with the second classes. So I start with SUN with the 2n plus 1 with the transform level 0. And then in this case, there is also in the middle a D5 brane. And then along this D5 brane, this fixed point for insertion of 7 brane is will be there. And then one of the A brane is attached, and it can be also taken to infinity by the Hanani-Witten transition, and this will be a decoupled S7 branes. And then the resulting theory, it turns out to be SPN with the 3 flavors. And then this is confirmed by the prepotential. As this is a G2 symmetry, we multiply 1/2 on the original one with identification of the Coulomb branches that is identified under these C2 actions. So this is a previous example that we mentioned. And yeah.
Could I ask a question about this prepotential calculations?
Yes.
So suppose you would turn on the mass deformations. Do you say like before the ZN quotient, you sort of can have a clear action of the ZN on the masses before the quotient, and then the additional mass terms, like the additional inserted D7s, stay sort of trivial under the ZN?
So I think, I mean, as I mentioned earlier, this in a generic point of the Coulomb branch, GN symmetry is broken. So we need to go to the special point. Probably the special point is where the putting all the masses to be 0, and then the prepotential analysis is done. Hello, can you hear me?
Yes.
Yes.
Okay, sorry that the connection was not very good. Okay, so where are we now? So Marcus, what I was saying is that the generic point on the Coulomb branch is GN is symmetry is broken. So we have to go to this special point, which is we need to control the mass parameters. And one of the manifest places probably where all the mass parameters turned off. So my analysis of the prepotential is done all the massless cases.
I see. I see. Okay. Thank you.
Am I sharing now or?
Yeah, you're sharing, but not in full screen yet.
Oh, okay. Sorry. Yeah.
Now it's perfect.
Okay. Good. Let me move on. So this is an example of Z4 folding, and probably this is a new theory. I mean, we call that pinwheel theory, which is a non-Lagrangian theory of rank 4, which looks like a pinwheel. And this one has the two discrete symmetry as a Z2 or Z4. And then in this case, the Z4 symmetry, we insert D4, and then this one of the 7 branes in this Z4 7 brane configuration is in fact can be moved to the other chambers, and if we put this 7 brane further, then it makes the actually SU3 with the transform level 2 with the 4 flavor. In this case, there is no free 7 branes or decoupled 7 branes. On the other hand, a Z4 symmetry case where the one of the 7 brane, this is A brane, is attached to this way, and this can be decoupled. So the resulting theory therefore has a decoupled seven branes. So the result can be treated in separately, and their prepotential analysis also perfectly agrees with this fibranes, the analysis.
Sung-Soo?
Yeah.
So in general, you would expect the global symmetry to be bigger than have no relation to the.
Okay. So I have So in general, the global symmetry. This is the rank of the theory after Zn symmetry. So usually, because it's divided by n, so the rank of the global symmetry will be reduced generically. But on the other hand, we are inserting some particular seven planes configuration. So depending on the rank of the original theory and their global symmetry, there may be the rank will be reduced or enhanced after the Zn folding. But if the rank is very big and the Zn is big, I mean you can guess from this generically the flavor symmetry rank should be reduced.
Okay, I see. Thank you.
So probably this is one of the interesting example, which is T4 theory with a Z3 symmetries. So T4 5-brane web is given as like this, and as before, we take the fundamental domain here and insert the 7-brane configuration associated with the Z3 symmetries. And here, our choice is that the edges has a charge of 1, -1, which is same as the B7 branes. And then this B7 brane can be decoupled by the Hana-Newton transitions. And the resulting theory is the theory without one of this decoupled theory. It turns out that the resulting theory is SU2 with a 7 flavor, with the 7 flavors. So the SU2 with the 7 flavor has the enhanced global symmetry of EA. We can check this result again by this analysis of the prepotential. It actually agrees. And also the rank of the flavor symmetry also suggests that the resulting theory should be also rank A. Therefore, I think at least within this 5-brane web and the prepotential configuration, we have the consistent theory, basically the Z4 theory and its G3 withholding give rise to SU2 with the 7 flavor, which has importantly has an EA symmetry.
Do you have an expectation? Can you say anything about the different states of the joint EA representation and how they arise in this configuration?
I do not quite understand your question. You are asking about this after Zn folding?
Yeah, I'm talking about this particular theory, right? Where you expect an E8, so you make a prediction that it's going to be an E8 symmetry. So there will be states in representation. So let's take the lowest state, the adjoint, and then I ask, do you have any idea how the states of the adjoint representation show up from the different states before folding?
I think you're asking for example, from this, how do I expect that there will be an EA symmetry? Is that right? Or
Yeah,
some
yes,
expect-
yes, yes.
One of expectation is that the we have a Z4 and a Z3 action, so we will have a SU4 symmetry remaining, and the insertion of E6. And in fact, we are losing the Hana because of Hana written. So we may have the E5 symmetry times a SU4, which can be enhanced to further to the bigger symmetry. And I think the possible the enhanced global symmetry probably E8, because it's starting from the SU4 times E5, which is SU5 SO10. And then if they are enhanced, and then the possible candidate is EA symmetry. I don't know whether it was
Okay.
So I mean, just by moving all the same branes inside this 5-brane circle, you can see the E8 same brane configuration. So E8 representation, they all come from the string mode connecting the same branes inside.
Okay, so you're saying that there are 7 states which would form the joint representation just because this brane system has E8 symmetry in 8 dimensions. Okay, and now the question. So then you would say there must be a current in the joint of E8 that couples to this.
That's right. Yeah.
And do you know the pattern? So, and the pattern of enhancement is like what Sung-Soo said, that there is an SU4 times E5, which.
At this moment, we couldn't identify the precise pattern for all the theories, but for the given theory, you can actually try to identify. But we don't have the general prescription how this enhancement occurs.
Okay, I see.
Right, so I will tell you the ZN case, but here you can also see that so the red one and black one, these 7 branes. So you look at the after this decoupled one, the remaining was the A5 BC, which is E5 or SO10 symmetries. And the other one, the original 7 brane actually has this A2 BC, which is SO4 symmetries. And then I would say that they are how they enhance to EA, and then rearranging can be seen in the EA symmetries.
Okay, I see.
So just one note is that this our result is actually is different from the this Acharya and the Lambert and other the papers, where this they expect that there's a E5 symmetry should be there, but we actually have more than E5 theory. We have the EA symmetries.
But surely both the Richard and Sung-Soo, they both did plenty of index computation. So what happens there?
Sorry,
it's not easy to carry out the index computation because we have to include the twisted sectors. You are right, but you know how to insert the twist sector effect. It's not easy one,
I see. I see. So you say there is a twisted sector.
Twist sector is coming from
because this is generalization of what is the orient fold. So as an orient fold, you have the twist sector in this case too.
But my experience is that orbifolds would have twisted sectors. Not
Orientable. What do you mean?
Is there a case of an orientifold with twisted sectors?
Yeah.
Mhm. Okay.
Yeah, localized at the singularity.
Yeah. But I know for sure for cases of orbifolds. Maybe there's for both. You have to take into account. Okay. Yeah. But okay, that's something to look at. Yeah. Okay. Thank you.
Okay. Let me continue. I mean, so I actually wanted to also show that there's a non-Lagrangian theory can be obtained by decoupling 9 hypermultiples from T4, and well, I think the idea is the same. So let me skip this one and let me move on to this T5 case. Here we have also can consider a Z3 folding. In this case, so there is a no decoupled 7 branes, whether this attached 7 branes to the original brane is through Hannah-Newton, it moves to the other chamber of the Coulomb branches. And the resulting theory is known as SU3 with the 9th flavor, with the 1/2 tensile level, or SP2 with the 9th flavor. This has the global symmetry of the SO20. Okay, here you can see that from the 7 brane configuration, where there's the A5, which is SU5 symmetry, which is the remaining after G3 folding from the global symmetry of T5, which is SU5 plus SU5, SU5 is reduced to SU5, and the insertion of this E6. In fact, there is the 7 brane that moves to the other chamber, so we will have this E5 symmetry, and together they are enhanced to a bigger symmetry to be a flavor symmetry of SO20. And then this theory also is also different from this the earlier work. So this is what I'm going to discuss more in the general case. So Tn case with the n is not a 3k, which is the case where the singularity located at the tip or on the vertices, and the flavor symmetry can be analyzed in this way. So again, as I said before, the flavor symmetry of Tn, which is SUN Q, is shrunken to SUN, and the insertion of this Z3 folding is because of the one is attached. One of the 7 brane is moved to another chamber or decouple. This breaks the symmetry of the E6 into SO10 times U1. So this is a generic, the expected global symmetry after G3 folding of the Tn theory, where the n is not 3 cases. So this is somehow we had a disagreement with these papers, where they claim that this E6 symmetry is broken to SU3, and the expected global symmetry is SU3 with SUN. So basically, the main difference is that whether this E6 symmetry is broken to SU3, or in our case is SU10 SO10 times U1. So this will be the sort of the discrepancy. So it will be good to have further study of this to resolve these discrepancies. So let me speed up a little bit, and then I'm going to show some of the examples, and then I'll wrap up this talk. So this is the thing that I mentioned earlier, that SU2 with the A flavor, which is the E string on this circle, has all the ZN symmetries, and ZN symmetry, and after this ZN symmetry is going back to this the SU2 with the A flavor itself, which can be also generalized to other interesting cases by adding more flavor to the TN theories, and make the this KK theories. And these are the examples. So let me skip these. And so I introduced two more examples to just show that 5-lane web can now deal with the two antisymmetric with A flavors. These are the SU4 theories with the 4 flavors on the one side and 4 flavors on the other side. And these are responsible for 2 antisymmetric matter. And they show the Z2 symmetries. And the resulting symmetry is give rise to rank 2 E string theory in a circle. And we also have the example of a matter in the triple antisymmetric rank, and also can be straightforwardly applied our insertion theories. So let me conclude. In this talk, I discussed the discrete symmetries and S-folding or ZN folding of these 5 DCFTs. And we discussed in the 2 different aspects, from the 2 different aspects. One is the based on 5-lane web, and that's and the resulting theory can be obtained. Another one is based on the prepotential, which is identified scalar parameters mapped to these under the ZN action, and they yield a consistent result. So the one of the important thing is that ZN fold and their ZN ZN fold introduces some particular 7-lane structures, which is associated with a D4, E6, E7, EA singularity, respectively to n equals Z2, Z3, Z4, G6 cases. So our analysis is based on this, in particular in the 5-lane web. We have 2 different classes on the fixed point exists on the face, or edges, or vertices. So both actually, as I said before, the consistent with the 5-lane the prepotential configurations. So as a future directions, one can maybe see the application of 6D series, maybe those that doesn't have the 5-lane webs, or some sort of other types of the discrete symmetries, not as maybe not as a one-form symmetry, maybe some other symmetries. Okay, so let me conclude the talk.
All right, let's thank Sung-Soo.
Thank you very much.
And do we have more questions?
Hi, Sung-Soo, can I ask a question?
Yes.
Actually, can you hear me? Because sometimes my headphone has very bad sound quality. So you can hear me clearly?
Yes.
Good. First of all, very nice talk. Thank you. And can you go back to the slide of the discrete agent of rank 1 theory with this table of all sorts of theories?
This one?
Yes, this one.
Okay.
I'm a bit confused because the superconformal field theory that local P2 leads to has no flavor symmetry. So what is the D3 that you are gauging from the field theory point of view?
So local P2 has no flavors. Yes, that's true. I have an example. This one. So
Yes.
I mean I think it should be not to be confused with the usual sense gauging. I'm doing the Z3 folding where the local P2 has the this Z3, and I mean the I am by folding, I'm identifying the three different the different boundaries and inserting.
I know from the brain web, it's very clear that where the C3 symmetry comes from. I'm just wondering from field theory, where is this C3?
I don't know. Let's see. So if you probably compute the like a what is it called? This partition function of local P2. And I think that there is a state that appears like 3 times.
Yeah, let me add a comment about this. So if you compute the superconformal buffer invariant and take the undefined limit, then actually you can see this kind of G3 symmetry which acts on each state. So first coefficient start from 3.
Yeah.
And second coefficient is 6 and so on. And actually we expect that at this moment we don't have a clear understanding how this G3 acts on the state. But at least on defined limit, you can see the degeneracy of the state, which is always multiple of 3. So yeah.
Right. Actually, this I think probably is related to the Z3 overflow point of in the modular space.
Yeah. From the P2 sense, P2 has a 3 fixed point, right? So this G3 will actually exchange the P2, but in terms of the field theory state, we have some interpretation in the undefined limit, but they are basically different state in the refined limit. So at this moment, we don't have clear understanding how this G3 react on the state.
Okay, thank you very much.
I think what Hicho was saying is that this, BPS state is to do with this. Here we have the Keller parameters, and they are actually the same Keller parameters. And so we have a degeneracy of 3. And then this is a BPS superconformal buffer invariant, which appears with the degeneracy 3. So therefore, in some case,
actually, yes. Now I recall that if you go to the overflow point in the modular space of the topological string, you also see clearly the symmetry.
Yeah, that's right. But this symmetry appears only in the undefined limit.
Right.
Okay, we have more questions. Right, then I'd say let's thank Sung-Soo again.
Okay, thank you very much.
Stop the recording.